Before we dive into designing a Kalman filter, let's make sure that we're on the same page when it comes to naming conventions. Since a robot is unable to sense the world around it with complete certainty, it holds an internal belief, which is its best guess at the state of the environment, including itself. As you may recall, a robot constraint to a plane can be described with 3 state variables: 2 coordinates, x and y, to identify its position, and 1 angle, yaw, to identify its orientation. These are its state variables, and we will denote a state with the bold letter x. States may change over time, so sometimes we will use a subscript to represent state x at time t. If you recall the 2 steps involved in the Kalman filter algorithm, they are a measurement update and a state prediction. Let's look at the first one. You know that a robot can perceive its environment using sensors, which produces a measurement. This is denoted with the letter z, and z of t represents the measurement obtained at time t. Next, our control actions, such as movement, can change the state of our environment. Control actions are denoted by u, and u of t represents the change of state that occurred between time t minus 1 and t. Perfect. Now that we've agreed on the naming conventions, let's go back to the Kalman filter cycle. We need to start the cycle somewhere, and this is usually with an initial estimate of the state. As you will soon see, the estimate does not have to be accurate. It can be an awful guess, and the Kalman filter will still manage to give us good results very quickly. Then, we iterate between the measurement update, where we gain knowledge about our environment, and the state prediction, which causes us to lose knowledge due to the uncertainty of robot motion. You will first learn to implement the measurement update, and following that, the state prediction. Throughout this time, you'll be working with a one-dimensional Kalman filter. However, after gaining a better understanding of how Kalman filters operate, you will extend your knowledge to a multi-dimensional Kalman filter and even code one in C++. Once you're a Kalman filtering expert, we will look at how the extended Kalman filter allows us to solve a wider range of problems and help us with real-world robot localization.